Hello, my name is Cameron, and I'm going to talk to you about property testing and the container method. And this is joint work with Eric Blay. So I'm going to give this talk kind of in reverse. I'm going to start by talking about our key technique, which is this graph container method. And I'm going to give a brief introduction to the technique. And then I'm going to talk about how we can use this container method to analyze property testers. And in particular, I'm going to go through a simple example. And then finally, I'm going to talk about some of our new graph container lemmas and how these can be used to prove new property testing results. Okay, so what is the container method? So the container method is a tool that can be used for characterizing independent sets in some graphs. So recall that an independent set is a set of vertices such that no two vertices are adjacent. So for example, this graph here has an independent set of size 3. And the container method roughly says that for any graph satisfying some nice conditions, which I'll talk about what this means in a minute, all independent sets in the graph are clustered together into a small number of containers. So in particular, there could be many independent sets, but they are somehow clustered into these containers such that the number of containers is small and the containers themselves are small. So for example, with this graph here, this graph actually has quite a few independent sets. So for example, this is an independent set, this is an independent set, and there's many others. But as it turns out, you can find these 3 containers such that every independent set in the graph is fully contained in at least one of these containers. So in particular, you can see each of these 3 independent sets is fully contained within one of these containers. So let's formalize this a little bit. The container method is usually phrased in terms of graph container lemmas. And these always vary depending on the intended application. But in order to introduce it, I'm going to go back to one of the first applications of the container method by Kleitman and Winston. And what they show is that for any epsilon and rho, let G be a graph where every induced subgraph of G on row n vertices has at least epsilon n squared edges. Then there exists a collection of containers where each container is a subset of the vertices. And so the collection itself is a subset of the power set of the vertices. And this collection of containers satisfies a number of nice properties. As I mentioned before, every independent set is fully contained in at least one container. Also, we have that each container is relatively small. So in particular, it's at most roughly rho n. And the collection itself is relatively small. So in particular, there could be like an exponential number of independent sets. But in general, the collection of containers will be much smaller than that. And so this condition here, every induced subgraph on row n vertices has at least epsilon n squared edges. What are some examples of graphs that satisfy this? Well, random graphs. Any induced subgraph of a random graph has a sufficiently high number of edges. It can also be shown that this is true for D-regular graphs. And in fact, this is one of the very common applications of the container lemma. And in our case, it turns out this condition is exactly what it means to be epsilon far from having a row n independent set. And I'll talk about this a little bit later. So these graph container lemmas have tons of applications across combinatorics. And the main reason this is because many problems can be converted into problems about independent sets on graphs. And even many problems that are not even on graphs in the first place, they can be converted to problems about independent sets. So if you're interested in this, I'll recommend these 2 surveys, which show a wide range of applications of this. But for the purpose of this talk, I'm not going to go into these applications. Instead, I really want to focus on how do we construct this collection of containers. And I think the best way to describe this is through a game. Suppose there's this graph and I have this independent set in the graph, which I've circled here at the bottom. But you don't know what this independent set is. Suppose I want to tell you the most I can about my independent set by only telling you one of my vertices. So I don't have time to tell you both of my vertices. I can only tell you one, and I want to tell you as much information as I can. What can I do? Well, if you think about it, one idea is I can send my highest degree vertex. And why is this useful? Well, any vertex that is adjacent to this vertex is certainly not in the independent set. So you can rule out these three vertices from being candidates of the independent set. So this is pretty good. I've told you one vertex and you ruled out three vertices. But actually, there's a lot more that you can infer from this. Because I've told you this is my highest degree vertex, any vertex with higher degree is definitely not in the independent set, because otherwise I would have sent it. So these three vertices here have degree 5, and the vertex I sent had degree only 3. So you can rule them out for being in the independent set. So this is kind of shocking. I've only told you one vertex, and you figured out exactly what my independent set is. Now, this is just a small graph, and this may not work on much larger graphs, but what we can do is we can repeat this procedure. So roughly, what would this look like? We're going to call this the container generation algorithm. And the input is a graph in an independent set, and we want to produce a container, which is like the candidates for being an independent set, and a fingerprint, where the fingerprint is the vertices that I'm sending. So what would this look like? Again, I would pick the vertex with highest degree in my independent set. And then you can rule out all the neighbors and all the vertices with higher degree, and you can get this smaller set of candidates for being in the independent set. And then I can repeat this. So I can send you another one, and you can reduce the size of this candidate set even further. And we can keep repeating this until we're happy with the size of this set of candidates. And at the end, we're going to call this the container of the independent set and the fingerprint of the independent set. Now, there's one very important observation here. The container is a function of the independent set. But based on this encoding view, if I just give you the fingerprint, you can determine exactly what the container is. And further, if you were to run the container procedure on the fingerprint, you would actually get the exact same container. So why is this? This is because if you were to run on the fingerprint instead of the independent set, when you're picking these vertices, the highest degree vertices, you would pick the exact same sequence of vertices as you would have picked if you were running on the independent set. Okay, so let's go back to this graph container lemma. I've just restated it here. So again, it says that if our graph satisfies this nice condition, then there's a collection of containers that satisfy these three properties. Okay, so on the previous slide, I described how to construct a single container for a single independent set. But this lemma talks about a collection of containers. So how do we construct the collection of containers? And it's actually maybe the first idea that might come to mind. We're just going to run the container procedure on every single independent set in the graph. Now, you might be thinking, there could be an exponential number of independent sets. So what are we saving here? There could be an exponential number of containers. But this is where we use the fact that we can use the fingerprints to define the containers. So this set is exactly equal to the set where we run the container procedure on every possible fingerprint. And now we use the fact that these fingerprints are very small, and so there can only be so many of them. And so in particular, if there's only so many fingerprints, there's only so many containers in this collection. And so that's roughly how we get that this collection of containers is small. I'm not going to go into the full proof of this, but this is just a high-level idea. Okay, now I want to talk about how we can use the container method to analyze property testers. And to do this, I'm going to go through an example. In particular, the independent set testing problem. So we want to distinguish between the cases that G has a row n independent set and the case that every induced subgraph on row n vertices has at least epsilon n squared edges. And this is usually called epsilon far. So this is epsilon far from having a row n independent set. And we want to do this by inspecting a small fraction of the input graph G. So this was one of the problems first studied by Goldreich, Goldwasser, and Rahn when they introduced property testing. And what they showed was that even though the general independent set problem is an NP-complete problem, this property testing version of the problem can actually be solved very quickly. So I'm going to try to show this by using the container method to analyze a simple tester. And I'll note this is not what Goldreich, Goldwasser, and Rahn did. They did not use the container method. They did something else. Okay, so what is this simple testing algorithm? What you're going to do is take a sample of vertices, of S vertices, and just check if the induced subgraph has an independent set of size rho S. And ideally, we want this S value to be as small as possible. And we're going to call it the sample complexity. Now, why does this tester make sense? Well, if the graph did have an independent set of size rho n, then when we take this sample, we should find a large fraction of vertices coming from this independent set. So the tester will correctly accept. The hard part is the epsilon far case. So in particular, we need to show that if G is epsilon far from having a rho n independent set, then in the random, when we take the sample and look at this induced subgraph, we need to show that this probably won't find a large independent set. And it turns out we can use the container method for this challenge. So I've just rewrote the challenge here. And recall the graph container lemma applies to graphs that are epsilon far from having a rho n independent set. And it gives this collection of containers. And with this collection, any independent set is contained in a container. And every container is relatively small. So what we can do is that for each container, we can upper bound the probability that we would get a lot of vertices coming from that container. Because the container is small, we can do this. And then we can just take a union bound over all the containers. And so using this rough argument, you can show a property test. You can analyze this property testing algorithm and show that it works with relatively small sample complexity. Okay, now I want to move on to some of our new graph container lemmas and give a high-level idea of how they give new property testing results. Okay, so first, here are some of our prior results on property testing using the container method. So we first used this main idea that I outlined to give a new property testing algorithm for the row independent set property. And then we used a similar technique to give a tester for K colorability. And again, both of these are these sample-based testers that just take a sample of vertices and check to see if the sample either has an independent set of size rho S or is K colorable for the K colorable property. And both of these results used new graph container lemmas, in particular, like strengthened versions of the container lemma I mentioned before. And also both of these results improved on the prior known bounds. In particular, the bound for the row independent set property nearly matches the best lower bound by Feige, Langberg, and Schechman up to logarithmic factors. But the main question is, what else can the container method give in property testing? And in particular, there's two interesting directions. First, we know from combinatorics that this container method has many applications to problems that aren't necessarily on graphs. So problems where we can map the problem into a problem about independent sets on graphs. So similarly, can we do this for some property testing problems that might not be on graphs at all, but we can map them into problems about independent sets? And second, both of these prior results are about testers that take a random sample of vertices, look at all the edges, like query all the edges in that sample, and then distinguish between the two cases. But what about testers that don't necessarily do that? So testers that are maybe a little bit smarter about how they query their edges. So in particular, instead of talking about the sample complexity, we can ask about the query complexity. So the number of edge queries made by the tester. So can we use the container method to study these types of testers? So our first result is a result for satisfiability testing. So first I want to define this. An instance phi of qk sat is a constraint satisfaction problem with q variables per constraint and an alphabet size k. And we say that phi is epsilon far from satisfiable if at least an epsilon fraction of the constraints must be removed to make phi satisfiable. And our theorem says that there's an epsilon tester for the satisfiability property with sample complexity kq cubed over epsilon. So in particular, this shows that we can use the container method to give a testing bound for a problem that is not on graphs. In particular, so we use a new hypergraph container lemma to prove this. And I'll note here that when we talk about sample complexity for these types of testers, this is a tester that takes a random sample of variables and checks to see if there's an assignment to these variables that does not falsify any constraints. And our result improves on the prior bounds, both of which had an exponential dependence on Q. And so our result is the first one that has a polynomial dependence on K, Q, and epsilon, and it matches the optimal epsilon dependence of the prior result. And this theorem immediately gives two corollaries. So first, we get a new bound for testing colorability on hypergraphs. And second, we get a new bound for epsilon testing any 0-1 graph partition property. So these are a class of properties that include K colorability and many other properties. And it turns out both of these types of properties are just special cases of the satisfiability property. So we just get these for free. And I won't go into any more detail on this for now. So I want to talk about roughly how do we prove this result. And we have to use a new hypergraph container lemma. And to do this, we have to encode the satisfiability instance as a hypergraph. And here's how we do it. For every possible single variable assignment, we're going to add a vertex to this hypergraph. And the edges correspond to falsified constraints. So in particular, if a set of single variable assignments falsifies a constraint, then this is going to be a hyperedge in the graph, in the hypergraph. So for example, suppose we have these three variables, x1, x2, and x3, and we have a constraint that says they must not all be equal. So if they're all equal, the constraint evaluates to false. Then how would we construct this hypergraph? Well, we add vertices for every possible single variable assignment. And then anytime this assignment falsifies the constraint, we're going to add an edge. So for example, if x1 equals 1, x2 equals 1, and x3 equals 1, then this would evaluate to false with the constraint. So we add an hyper edge. And same thing if all three values are equal to 2. And the important observation here is that in this hypergraph, satisfying assignments correspond to independent sets in this hypergraph. And further, partial satisfying assignments, so assignments to a subset of the variables that satisfy all the constraints that they are part of, also correspond to independent sets in this graph. And now using this encoding, we prove the following hypergraph container lemma. And this is just informal. Suppose phi is epsilon far from satisfiable. Then there exists a collection of containers where each of these containers is a subset of the vertices of this hypergraph. And this collection satisfies some nice properties. For every independent set in the hypergraph, there is some container that contains the independent set. And each container is small, and the collection itself is small. And again, this is going to be useful when analyzing the satisfiability tester, because what does it do? It takes a sample of variables and checks to see if there is an assignment to those variables that doesn't falsify any constraints. And this type of assignment corresponds exactly to independent sets in this hypergraph. So we can use this to analyze our tester. Okay, for our second result, we go back to the row independent set property. But this time, we study the query complexity of testing this property. And what we study is a new algorithm that gives query complexity rho to the 5 over epsilon to the 7/2. And so how does this compare to our sample-based tester? So what is that? Remember, our sample-based tester took a sample of size roughly 1 over epsilon squared, where epsilon is the main parameter we're focused on. So it took a sample of 1 over epsilon squared. And that means that its query complexity is like 1 over epsilon to the 4, because it just queries all possible edges in the sample. And so what this shows is that we can actually do better than this query complexity of the sample-based tester. And this type of gap is not known for very many graph properties. And we prove this via a new graph container lemma for an object we call independent set stars. So before I talk about these independent set stars, I want to talk about what does our tester actually do. So recall, our old tester just took a sample and checked if there was a large independent set in the sample. But this time, we want to be a little bit smarter about how we query our edges. We don't want to query all the edges in our sample. So this time we're going to take 2 samples. Take a sample S and a smaller sample R from inside of S. And this time, we're going to query all the edges in R and all the edges between R and S, but we're not going to query the other edges in S. And we're going to accept if and only if the set R contains a relatively large independent set and the set S contains a relatively large set such that there's no edges between these vertices and the independent set. So in particular, we're going to accept if there's a large independent set in R and a set of vertices in S such that there's no edges between these 2 sets. And I've used the dotted lines to illustrate that there's no edges between these vertices. So why does this tester make sense? Well, again, if the graph did have a large independent set, then both our R sample and the S sample should find relatively large fractions of this independent set. And in that case, will of course find a large independent set in R, and these vertices in S that are from the large independent set will have no edges to these vertices in R. So it will correctly accept. And as before, the hard part is showing that if our graph is epsilon far from having a row n independent set, then it probably won't find this type of object in the sample. And to analyze this, we introduced this object called independent set star. So we say a pair of subsets form an independent set star if I is an independent set and there's no edges between any vertex in I and a vertex in J. So in particular, these vertices in the middle form an independent set. There's no edges between them. And all the vertices around the outside have no edges to anything in the middle. But we don't care about edges between these vertices on the outside. And so this object is actually exactly what we were looking for with our tester. So this is like the inner vertices, the independent set, and these are like the outer vertices of the independent set star. And what we show is a new container lemma that roughly says that if G is epsilon far from having a row n independent set, then there's a collection of containers that cover all independent set stars. And this can be used to show that when our graph is epsilon far, then it won't find this type of object in our samples with high probability. So to summarize, we've shown that new graph and hypergraph container lemmas can be used to show a number of results in property testing. So the prior results use this to analyze the sample complexity of two graph properties, the row independent set property and the K colorability property. And in this work, we extended this to the satisfiability property, so a property not on graphs, as well as studying, again, the row independent set property, but this time the query complexity. And we gave a tester that has a smaller query complexity than the optimal sample-based tester. Thank you for listening.